Lay it on right along, girl. I tell you what, I put it on, girl. I'd put it on vinyl. A little rock, a little Motown. You got that baby pull me close sound. You make the whole room go round and round like vinyl. What we got is a little old-fashioned. Baby, you're an instant classic. They don't make them no more like you. So let the needle drop and play it all night. Might have a little static, but it's alright. Ain't nothing gonna stop this groove.
Well, good afternoon. I wanted to say third time's the charm, but this is like the sixth time I've started trying to record this lecture, so let's hope it works this time. Having major problems on this end with the Panopto recording app, so my apologies. I had this thing recorded actually last night, went to bed, woke up and discovered that Panopto had not recorded half of the slide feed, and then they synced up wrong. When I did it again this morning, didn't get the video feed from my end on the camera, and then had a few false starts since then. But hopefully this will work this time, and clearly if it doesn't, you won't see this version anyway. Hope everybody is doing okay out there. Hope you're having less tech problems than I seem to be having today. And welcome to lecture 36 of the 40 that we go through here in Physics in Everyday Life. So last time we talked a little bit about how lenses work. First of all, we introduced a new way that you can look at the behavior of light through a system by tracing what are called light rays, basically just straight lines that show you the direction that light's moving. And this is a convenient way to do ray tracing and to trace the path of some of the light through a system and figure out what's going to happen as a result. So specifically to lenses, when light goes from air into glass, or broadly, I guess, to any medium change, light gets refracted, which means it gets bent off of its current path. And the angle that it gets bent at and the direction that it gets bent to depends on whether you're going into a material that has a higher index of refraction or a smaller index of refraction. But when you have a converging lens, a lens broadly that's shaped like this and light passes through, it gets bent down towards the focal point of that lens. When you have a diverging lens, which has an opposite profile, light gets bent away from that as if it was coming from the focal point on the other side. And either of those can be used to correct vision problems such as nearsightedness and farsightedness. So because this lecture is about capturing and recording sound, which is super ironic given that I'm having so many difficulties capturing and recording this video and sound, I thought that we could start with actually capturing a sound wave. So I poked around and there seemed to be free internet apps to do so. Who knows, maybe I went to this thing and compromised my computer and this is why I can't record any lectures. I don't know, but I used onlinevoicerecorder.com. Sounds legit, right? And I recorded this little snippet of sound. Physics. And obviously couldn't think of anything more clever to say than that. That's the word physics, but pictured as a sound wave. And so you can see that at different points during this my saying that word, you get different little squiggles or peaks in this waveform, which, if you're a curious person, might lead you to ask questions like, what's happening when you create sound? Now, we've talked a little bit about that back in the sound and musical instrument lecture from earlier this semester, so I'm not going to revisit that too much. More, we want to focus on how do you actually capture this sound? How do you store it if you want to play it back later? How do you share it with others? So a brief history of some of the technology phases that this whole industry has passed through and the relevant physics principles that are connected. So back when we did the lecture on sound and musical instruments, we looked at this little simulator in PhET, and I'm not going to ask you to do so now, though you're certainly welcome to go play around with this Making Waves simulator. This is the sound tab in that simulator, and you may recall that when you use this simulator, the speaker moves back and forth and it produces these pressure waves that move out through what the simulator is symbolizing as little molecules that are in the air, those little white and red dots. And so the molecules themselves shake back and forth locally, but they don't actually move across the screen. It's only the wave of pressure that moves across the screen. And so if you click one button in that PhET simulator, you can bring up a pressure wave, and it draws the little pressure wave for you as the wave is traveling across. Here's another representation from a different textbook. Again, the picture is that we have air molecules that are compressed more tightly in certain regions, spread out more loosely in other regions. And so when there's increased pressure that's above atmospheric pressure, decreased pressure is below atmospheric pressure. And so even though it's the air particle movement that's happening here, we can sketch a pressure wave to symbolize what's happening with pressure as a function of time. And that's one picture of what we're picking up when we get that sound wave that we captured previously. So sound creators like me talking or like you listening to whatever music you're listening to generate changes in air pressure, and those changes in air pressure move outward as these sound waves. But how do you actually record this and store it for later use? Well, before we get into that, just a little bit of review. What types of waves are sound waves in air? So this is the first of the 3 Poll Everywhere questions that we have for this lecture. The link to the Poll Everywhere survey is here if you're following along on the Google Slides, or it was linked in the lectures folder as well. So are they longitudinal waves, transverse waves, or a combination of the two? Now, truthfully, lots have happened since we talked about this in class. This was back, I believe, in lecture 24. So to help you out a little bit, I brought in those definitions. In a transverse wave, the displacement of the medium is perpendicular to the direction that the wave is traveling. And in a longitudinal wave, the displacement of the medium is parallel to the direction that the wave is traveling. So the first era of what we would consider recorded sound started in the, late 1800s, the 1870s. So if you are a student of history, you'll know this is when the Industrial Revolution was getting going and really transforming the way things were done in America and elsewhere around the world. One of the first devices that's recognized as a sound recorder is this device called a phonautograph, which was made in the late 1850s. And I do not recall the inventor's name, but an interesting device. You had a big sort of, cavernous hole here that was open at this end that you could project your sound into. And the whole point of this was to try to focus the sound waves down to this end where they would hit against this diaphragm and make this diaphragm jiggle back and forth. Well, that diaphragm was connected to a stylus. You can think of it as a pen. And so when it would jiggle back and forth, that pen could sketch out a drawing of what the sound wave looked like on a piece of paper, tape, or I'm not even sure what they used, that could be spun past the stylus on this little turn wheel here. And so I believe I read that the inventor of this phonautograph simply wanted to see what sound looked like when it was transcribed in this fashion, and didn't have any idea of actually, when you record something in this fashion, there's the possibility of using it in the other direction and actually playing recorded sound. Well, you can play recorded sound if you have some way of, recording that information. And so somebody thought, hey, if we actually, instead of just writing this down on a piece of paper or paper tape or whatever it is, etch it into something soft, we should then be able to make the stylus trace that path again later and reproduce the sound back. And that's the basic idea behind Edison's phonograph that came out in 1877. They messed around with different materials, such as, I think, sort of thin metal foils and the like, but ultimately settled on a wax. And so what would happen is when you recorded this sound, you would shout into a device, not dissimilar to the phonautograph over there. Those would create little sound waves in the diaphragm that would be amplified by the stylus. They would be then etched onto a wax cylinder that was being turned through this device. And then later on, you could send a similar stylus through the grooves on that wax cylinder. That would make things jiggle in the same fashion they had when the sound was recorded. And if you connected that to some sort of amplifying diaphragm, you would get the sound back out of the system in a phonograph. So over at right, picture of Edison with part of his device there. And this is a up-close photograph of what the grooves on those wax cylinders looked like, not too dissimilar to the lower picture there, which is the grooves on a vinyl record, which came along a few years later. So I found this video particularly fascinating, and now I'm going to get to watch it for the fourth time. But this is some folks from the Metropolitan Opera in New York experimenting with just such a system. Or it would be if it would play. Here we go.
A little scratch. There's not much choice with this. So.
Yeah, I see the end. When it was loud.
Yeah.
It's.
You see a lot more.
Yeah.
Yeah.
A lot more. Okay.
So as you can see, not a system that has the audio fidelity that we're used to today, but not terrible in terms of capturing the sound, and certainly revolutionary if you'd never been able to hear music like that before, and suddenly you would have access to recordings of the opera in your little town when you'd never been able to travel to somewhere like New York. So I have a poll everywhere question, and this is one you can't get wrong. It's just an opinion question. Truthfully, you can't get any poll everywhere question wrong because we're just tracking participation, but my hope is that you are giving it your best shot on the questions that actually ask you about the content. But, wax cylinder recordings had various drawbacks, and so I've just put a few down on the list. Which of these would be the most troublesome to you? The fact that the wax cylinder could only play 2 or 3 minutes worth of music, because that's how much sound you could get on that cylinder before you ran out of real estate. The fact that they would wear out after a few dozen playings, so maybe you listen to your recording 20 or 30 times and then it's no longer, excuse me, no longer recognizable due to the soft wax that's on there. Or that you would have a limited frequency range. So we've talked previously about human hearing ranging from about 20 hertz or 20 cycles of oscillation per second up to 20,000. Well, these wax cylinders could only record frequencies down to 100, maybe 200 hertz in the lower range, and then up to maybe 2,000, 2,500 hertz, something like that. And so you would lose clearly lots of bass in that recording and lots of really high treble. So obviously that would change the mix of the sound that you were listening to. Well, so after this, the mechanical innovations continued and people continued to make these things better and better and better. It's broadly something I think that's happened with any sort of technology that gets introduced, right? The first computer is huge, it's a room, but people keep working at it and make it a smaller and smaller and better device. Same thing here. So the mechanical era of recording sound was not gone. In fact, it evolved. And the wax cylinders were soon replaced by flat discs. And then somebody figured out that you could use vinyl for the flat discs. And that's the LP records that may be still lying around in your parents' or grandparents' houses. Maybe some of you have them because you like vinyl sound better. They still make them today. But in the 1920s, 1930s, 1940s, lots of innovations with electricity and magnetism came along. And they also played a key role in revolutionizing the way that sound was amplified and transmitted. So along this time was the first microphones. Actually, the first prototype microphone came out somewhere in the 1870s, kind of when they were making these early recording devices as well. I believe it was a ribbon microphone, if I'm remembering correctly. But people continued to play around with different kinds of microphones and innovations in microphones all through the turn of the century. In 1924, the first dynamic speaker was developed by Kellogg and Rice. And the dynamic speaker actually worked the same way as one design of microphone worked. So we're going to talk briefly about two different kinds of microphones here and then comment about the speaker. So one kind of microphone still in use today is called a condenser microphone. And a condenser microphone has a diaphragm that moves as the sound wave hits the diaphragm. It makes it oscillate. And if you make that diaphragm out of a conducting material, and you make this rigid backplate out of a conducting material, in truth, you've made a capacitor. So we've talked before a couple of times about a parallel plate capacitor. If I have this parallel plate capacitor and a sound wave makes the top plate jiggle, if I've previously charged up this capacitor, that jiggling in position between the plates of the capacitor will actually make the potential difference, the voltage between those two plates, oscillate and form an electrical wave that mirrors the properties of the sound wave that created it in the first place. So you are converting a sound wave in air particles into a voltage wave. Another kind of microphone is a dynamic microphone that uses an electromagnet. Same basic kind of idea. You are going to make something wiggle by the sound waves that come in. And in this case, the thing that's wiggling is the diaphragm that's out in front of this. And inside is an electromagnet. Well, an electromagnet and a permanent magnet. In that, you have a permanent magnet here. And it doesn't matter which one you connect to this. But let's just say the permanent magnet is connected to the diaphragm out front. Okay, when a sound wave jiggles the diaphragm, it's going to jiggle this permanent magnet that's within the coil. And what that does is it actually induces currents within the coil that move back and forth depending on which direction this magnet is moving and how fast it's moving, how much amplitude there is to its motion, all those characteristics. Again, you're taking a motion pressure wave and converting it into an electrical wave with a changing electric current within the coil. That dynamic microphone, by the way, is basically the same principle behind the dynamic speaker. What you do in a dynamic speaker instead, though, is you connect this coil to your electrical signal that you've gotten from somewhere else, like your microphone. And when you send the electrical signal through the coil, when the current's moving in one direction, it makes a magnetic field in one direction, and it pushes the magnet in one direction. And then if the current switches direction within the coil, it's going to pull the magnet back in the other direction. And these changes in current can oscillate the microphone, or the magnet rather, back and forth. And that magnet, if it's hooked to some sort of paper cone, is going to jiggle it back and forth and produce the sound that's in the speaker coming out on the other end. So a dynamic microphone and a dynamic speaker are actually one and the same device. They're obviously engineered for their specific purpose, but you can actually use one as the other. And I remember being, 13 or 14 years old and figuring out that with an old pair of headphones, I could use one as a microphone connected to a speaker to produce sound. You can also use a microphone as a speaker, but the microphone is so small that you generally get very, very low volume out when you are trying to do that. So again, these electrical innovations didn't replace the mechanical era of recording sound, and record players and the such continued to be refined through this whole era. It's just now that you had an ability to amplify the sound and to receive the sound and transition it into an electrical wave via these electrical technologies. Well, actually before the 1940s, some technology that evolved into this magnetic era of sound recording was developed. So magnetic tape was actually first made in the late 1920s in Germany. And apparently during World War II, the Germans used this technology to store information. And I've heard or read that the Allied forces sort of knew the Germans had this technology, but they did not themselves have the technology at the time. And it was only through going through post-war Germany after the war was over that this was discovered by folks from the United States. But it quickly revolutionized the way that sound was going to be recorded, because now you could make a paper tape or a plastic tape or whatever kind of tape you wanted, coat it with a material that could be magnetized, and voila, you had a system for recording information, sound and other, but our focus here is just recording these sound waves. So magnetic tape is generally a plastic strip, and it has a magnetic side to it. You see them in the cassette tapes, which you may have some experience with. They're kind of dying and on their way out, but we've got a box of them in here because we're old people and we could still remember the time when tapes were exciting because you could carry them around. You could put them in a Walkman. They were not a big vinyl record. And so you can see if we hold that up to the camera there that there is a magnetic strip that runs down there on the bottom of the tape, and then it's wound around these reels. And that can be used to record music. The same basic technology, by the way, is in the music and picture recording technology of the VCR, the video cassette recorder tape, and even in the magnetic storage devices that are still in many computers and were very common in computers up until a few years ago when some solid-state drives started replacing them. So the broad principle is that you need, when you're going to write this information onto a magnetic tape, you need some sort of magnetic head. And there's a couple of different ways these magnetic heads are engineered to either record in a longitudinal fashion or a perpendicular fashion, but the principle is really the same. If you have your sound that's been encoded in this electrical wave and you send it into what can be an electromagnet, the amount of current that you send through there is going to determine how strong your electromagnet is and what direction the magnetic field is in. And while you're changing the magnetic field in that electromagnet, if you are passing magnetic tape underneath, that magnetic tape is going to record a record of which direction the magnetic field was in and how strong the magnetic field was in when it was in the location of the magnetic head. And so this system can be used to store information in a binary format, and we're going to talk a little bit more about binary numbers here coming up shortly. But it also can record things in an analog fashion, because just like a compass needle, so if you have a compass needle points in one direction or the other, I can actually get the compass needle, which is my magnet, to point in a variety of different directions, right, depending on where my magnet is. And so I could lock in, quote unquote, that magnetic information, if you think about those domains just being little compasses oriented at various angles to record different amounts of this sound information that was being fed there. Then to play it back, you do the reverse, right? You put the magnetic tape in a device, and as that magnet is passing underneath, it's going to alter the magnetic field, and you can electronically engineer it to then produce a electrical wave that mirrors the information on the magnetic tape and connect that to a speaker and generate it back into a sound wave. Well, in your lifetime, and certainly in my lifetime, we've all lived in what's known as the digital era of recording, and this has once again revolutionized the way sound is stored, transmitted, shared, and recorded. So the first compact discs were developed in the early 1980s, so probably before your lifetime, but not before mine. I was a 9-year-old kid in 1982. And CDs, came out, and the first CD players were, like every technology, were horribly expensive. The first CD players in your car were terrible because the CDs skipped all the time, but eventually people kept engineering these things and getting them better and better. Well, a CD, if you look at it, right, you can see just the rainbow of colors there. But what you really have on the surface, if you get down and look at this through a really good magnifying glass or perhaps a microscope, is a whole series of little pits. And what the region in between those pits are called lands, the flat regions within this CD. And so we're going to think about a few questions here related to CD operation in the next couple of minutes. First, how do you turn sound, this pressure wave, into digital information, into just a series of numbers? When you do so, how do you get it on a CD? Why are CDs optical? Why do you need light to make a CD work? And how do these optical drives, CD players, DVD players, Blu-ray players, all the same basic technology, how do they actually read the discs and get the information back out that becomes the sound that you are listening to or the video game you're playing? Well, let's think about turning an analog signal into a digital signal. So remember that wave back at the beginning where I said the word physics? I got a whole bunch of little squiggles like that. Well, if I was able to zoom in on one of those squiggles, I might see something kind of like the waveform that I've sketched on this slide. Truthfully, it wouldn't be this. I just scribbled this in the Google slide, but you get the idea. So I'd be seeing these variations in pressure over time. And if I pinned on a grid here so that I could do some conversion, what I could do is go along each of the vertical lines on the grid and see how high is my pressure wave on that vertical line. And then that becomes a number, and now I suddenly have this chain of numbers that encodes the information that was there in the wave. So if I look here, my first vertical line on the slide, the pressure wave is somewhere between 1 and 2 units above there, but it looks closer to 1, so I'm just going to call it 1. Then I get to this next one. This is about 1 unit below the equilibrium. This next one is right at the equilibrium, it looks like, even though it looks like I encoded it as a 1 in mine. Up here, I'm at about 4 units above, 2 units below, close to 5 units below. So you can see I'm turning this into a whole series of numbers here, even though I'm not transcribing it entirely faithfully. So that's the series of numbers that I've turned my wave into. And how good, or I guess how much audio information you encode is going to depend on how often you sample. So how often do those vertical lines come along? And furthermore, how many individual heights do you allow? So on mine, I had just 10 boxes above and 10 below. But if I had 10,000 above and 10,000 below, I could measure this wave much more precisely. All right, so now I have a series of numbers, and technically that is a digital signal now. But I want to convert this into something that I can encode onto my CD. Well, one of the problems right out of the gate is I have some negative numbers, and I don't really know what to do with those negative numbers in terms of turning them into a binary number. So I'm going to arbitrarily just do something here and add 10 to all of my numbers. Again, I'm encoding, and then on the other end I'm going to have to decode. So as long as the decoders and the decoding device knows what was done on the encoding end, you can get all of these things to work out. So now I have this whole series of positive numbers, and I'm going to code those into digital numbers using the scheme that we first talked about in the compasses and credit cards lecture a few weeks ago. So you may recall, but in these numbers, which are 4-bit numbers, the rightmost number is the ones place, because that's 2 to the 0, which has a value of 1 in base 10. The second bit here from the right is the 2 to the 1 place, or the 2's place. 2 to the 2 is the third digit from the right, that's 4. 2 to the 3, which is 8, is the fourth digit here. And I only need 4 digits to encode all of these particular numbers. Much more commonly, you have at least 8 of these digits to encode numbers, but I kept the range small here. So 11 is going to be 2 to the third plus 2 to the 1 plus 2 to the 0, or in base 10, 8 plus 2 plus 1, which gives you 11. 9 is 2 to the third plus 2 to the 0, or 8 plus 1 is 9. And so you can see I get all of these things encoded in here. 5, for example, 2 to the second plus 2 to the 0 is 4 plus 1, and that gives you 5. And all of these numbers are now encoded in binary information. What's the advantage to the binary information? Well, when I transmit that information, the reader only needs to know whether the system is on in the 1 state or off in the 0 state. Here's a little thought experiment. Wherever you are, if the lights are on, it would be fairly easy for you to tell if the lights were on or off, right? Those are the 2-state possibilities there. But if somebody has a dimmer switch connected to that light, and they are secretly just manipulating the dimmer switch back to brighter and dimmer, you would have a much harder time quantitatively describing, oh, there's 40% brightness in the room right now, there's 78% brightness in the room. It's much easier ultimately if you can just say off, on, off, and have that information, and then decode it back on the other end and turn it into the ultimate wave. So this is kind of how lots of digital systems work. They're looking for systems that can be in one state or the other, like the north or south poles on our credit card strip. Or here, an electrical signal that is either on and sending an electrical current, or off, or in a high voltage state or in a low voltage state. Anything that has an either or setup. So now we've got this information. How do we put it on a CD? Well, first, the last question in our Poll Everywhere survey, just so that you can practice your binary conversion. If we have pressure readings that coded out to be 11, 13, 3, and 8, what would they encode in as binary? And you've got 4 choices of 4 sets of numbers on this question. So back to our CD. Our CD is actually this sandwich of different layers. Let's talk briefly about what's in each layer and how they function. So the lowest layer, the layer on the back of the label side, is just a layer of hard plastic. It's made of a polycarbonate material. And importantly, it is, fairly durable, though they do get scratched, and it's transparent to light. I need light to be able to travel through it. Now the light slows down in the polycarbonate material because it has a higher index of refraction than the air, but it can get through. It's transparent. The second layer is usually in CDs a thin layer of aluminum. In things like Blu-rays and DVDs, sometimes they're made of gold or some other sort of metal, but the aluminum is a reflective layer because the light will mostly bounce off of the reflective layer of aluminum here. And the aluminum layer is where it's encoded with all of these pits, these regions where it's lower than the surrounding region, and then the flat land in between all of the pits. Then you have a thin layer of lacquer on the other side, and that's again like a plastic-like layer, and its primary purpose is to protect that aluminum layer from getting oxidized, rusted if you will, though rust is technically only iron being oxidized. And then you have a label, so you can write things like Arizona trip number 1 on it, and then finally you have a laser down at the bottom. Very often in CD players, these are small diode lasers. And its job is to produce a laser beam that you shoot up at the compact disc and then is going to come back down in some situations. So if you've ever looked at a CD drive or an optical drive in your computer, usually they have somewhere that is a spindle that holds the CD, though if it's one of those that's just a slot where you put it in, that's all accomplished for you in behind the curtain. And then you have at least one, but very often 2 or 3 of these lasers. And if there are more than one laser, usually one laser's job is to read the information off the disk, and the other's laser's job is to steer, if you will, to make sure that you are where you need to be on the disk to read the information. So broadly, you need at least one laser, and it shines a beam upward at a spinning disk. And what happens to that beam after it hits the disk depends on where on the disk it hits. If you hit in a place where there is a pit, depending on where you look, there's a couple of different explanations. Some people say just the pit scatters light all over the place, which it probably does, particularly since it's not going to be uniformly engineered on its inner surface there. But it also is manufactured at a depth so that any light that goes in and hits the pit and then is reflected, compared to light that hits an adjacent land and is reflected, when those two rays of light come back down, their waves actually add together destructively to partially or completely cancel out the light. The big point of this is whether it's scattered or destructively interfered, you're not getting much light going back down into where the laser beam came from and getting read by the photodiode that in this artist's depiction is this little detector over here on the left that says yes, there's light, or no, there's not light. When, however, the laser beam just hits the nice reflective flat land surface in between the pits, that light is reflected back down and detected by the photodiode. And so basically, when it's hitting a pit, the system is reading a 0 state. When it's hitting land, it's reading a 1 state. And in that digital information, you can encode all the information that is in your sound file to play back. Obviously, the CD player has to know the code because it turns that digital code back into an analog electrical signal, and then that analog electrical signal connected to your speaker vibrates an electromagnet or whatever is making up your speaker to produce the sound waves on the other end. So that's what we wanted to talk about in this particular lecture, and boy, I'm getting a little tired of it, so I sincerely hope it worked this third time. We talked a little bit about sound recording and playback, which sort of went through different eras in our history. First were devices that worked on just mechanically moving styluses and recording that information in some sort of soft medium and then tracing back through it with a similar stylus to produce a sound wave on the other end. But when we had the ability to capture an electrical signal, things moved forward with the development of microphones and speakers and the ability to turn a sound wave into a wave of oscillating voltages. Moved forward again in the 1940s and forward with the ability to store information on a magnetic tape and steer those magnetic domains to encode the information. And finally, in recent years, to digitize information and store them in a series of ones and zeros. First on the CD, but in other forms, as we'll see in Friday's discussion. So laser beams in optical drives shoot up on the bottom side of these optical discs, or the top side, I guess, depending on how you think about them, go through a transparent layer, reflect off of a reflective layer in there, and can read whether they've hit land or a pit and use that to convert that back into a digital signal that can then be processed back into an analog sound wave. So this is the discussion that lines up with section 14.2 in the textbook. If you've not looked at that, I would suggest you do so. Bloomfield goes into a couple of examples that I didn't cover, such as what makes a DVD and a Blu-ray different from a CD. If you find them helpful, I'd encourage you to work on the Chapter 4 recommended practice problems. 14 recommended practice problems. 4 was a long time ago. And we will be talking about the content of Section 3 in Chapter 14 on Friday. Have a good day, everybody.